While observing the activity of the bank vole at a location on the west coast of Scotland, a serious problem arose in the form of fogging of lenses of the trail cameras being used. At times, overnight images were degraded by condensation on both the main camera lens and any close-up lenses that were used. This was a result of their temperature dropping below the dew point. Now, methods are available to reduce condensation, such as coating the glass with a surfactant, such as dish soap, but such methods were found to be inadequate in the present context in the long term. An alternative approach is to raise the temperature of the glass, and so it was decided to develop a lens electric blanket. This shows the effect of the condensation on image clarity. Identification of the presence and species of rodent clearly can become impossible under such conditions. The camera model used for this project was the Campark T100, which has the advantage that it can be operated by Wi-Fi, including real-time monitoring of the camera view and inspection of recorded images. It's also ideal for mounting close-up lenses, as the main lens is contained within a tubular, albeit slightly conical, projection, which simplifies push-fitting a tube in front of the lens. Now this shows the components forming and controlling the electric blanket. This white plastic tubing is a push-fit onto the main camera lens projection. It originates from the cap of a toothpaste tube and is slightly pliant, enabling it to be also push-fit, or slightly screwed onto the thread of a 25 to 37 mm step-up ring. The other end of the ring can take a close-up lens or no lens at all, as required. The heating filament is ribbon-shaped and can be wrapped around the tube. The undersurface of the filament is adhesive, but a narrow cable tie was also used to consolidate the filament, the electrical supply wires and the thermistor. The thermistor terminals had been previously shortened, soldered to their electrical supply wires, and waterproofed and insulated with hot glue before clamping it onto the filament with the cable tie. Now, ideally, the thermistor would be placed in contact with the lens glass, but that is really impractical. Other models of trail camera may not be so compliant when it comes to fitting additional features, so it may be necessary to use putty and/or use coated filament wire, or perhaps consider attaching the filament to the camera body. Once all the wiring was connected to the plastic tubing, the tube surface and back of the metal step-up ring were liberally coated in hot glue. Now this further consolidated the unit, as well as providing waterproofing. It would also improve thermal conductivity and possibly provide a degree of thermal insulation. Temperature control is provided by a 12-volt mini thermostat, which is capable of providing 12 volts to the heater. However, this would be power-hungry, and nothing like the 12 watts at which the heater filament is rated is really needed. Use of a switching voltage regulator or buck converter is an efficient way of reducing the 12 volt supplied by the thermostat. This shows the circuit diagram for the system. The thermostat is actually sold with a temperature probe containing a thermistor, but it's unsuitable for the present application, so cut it out and attach its leads to the recommended model. The thermostat functions as a switch between terminals K1 and K0. You set the desired target temperature using buttons, and once the temperature falls below the target, K1 and K0 become connected, resulting in 12 volts to the buck converter. In fact, it's not quite as simple as this, because you can set a hysteresis value as well. By default, this is 2 degrees, which is probably okay to leave for the present application. What this means is that the temperature is allowed to fall by 2 degrees below the target before the thermostat relay connects K1 and K0. The heater has a resistance of 12 ohms. If the buck converter output is adjusted to 3.3 volts, this results in the heater operating at 0.9 watts, which has been found by experimentation to be adequate for rapidly maintaining target temperatures in a very cold ambient condition. A consumption of 0.3 watts by the heater has been found to be insufficient in typical temperature conditions. This would be produced when operating at around 2 volts, so the minimum voltage output by the buck converter will lie somewhere between 2 and 3.3 volts. The physical manifestation of the circuit is shown here. The 12-volt supply can be from a battery, or better, from a mains adapter. Based on measurements, the circuit draws 15 milliamps when quiescent and 170 milliamps during heating episodes. Now, battery life will depend upon the duty cycle and temperature conditions throughout the day. But, for example, a 20 ampere-hour 12-volt battery might be expected to supply enough power for around 14 days, but this hasn't been tested. For garden applications, a mains extension cable supplying power to both the camera and the heating is a good solution if it's practical. But does it work? Now, when it comes to testing the system, the overnight condensation episodes had abated, and I had almost given up testing. But one May night, at around 2 a.m., I looked at the recently taken images, remotely from my office via Wi-Fi, to find that they were ruined by an accumulation of dense tiny droplets. Well, I hadn't been expecting such conditions, so the heater wasn't operating. I switched the system on and at the same time placed a second identical T100 camera alongside and set both cameras on time-lapse. This shows the difference after 2 hours, although it was similar after just 1 hour. The electric blanket cleared the condensation, producing perfect images, whereas the other camera suffered significant degradation for several hours. On this occasion, the thermostat target temperature was set at 12 degrees, so switched on after a fall to 10 degrees. A significantly lower target temperature may also be successful and will consume less power, but this hasn't been currently tested. An interesting result from this comparison is that there was a difference between the core temperatures recorded by the two cameras, with the heated model 2 degrees centigrade higher. These cameras have an inbuilt temperature sensor mounted on the motherboard, so it appears that the heating element has more than a localized effect on the temperature of the camera.